Hello everyone, welcome to my session. I am Ensar Basri Kahveci. I work at Hazelcast as distributed systems engineer. Just a quick poll before we start. Anyone familiar with Hazelcast, using it or check the documentation project? Cool. Yeah. In fact, you do not have to know anything about Hazelcast for this session. So it is the leading in-memory data grid, open source in-memory data grid written in Java. So in simple words, it's a distributed data structure cluster. It gives you distributed implementations of the collections and concurrency APIs of Java, like maps, set, list, log, semaphore, etc. So in our new version, we implemented a new version of these concurrency primitives that are familiar to us from the Java development, like logs and semaphores. So today, in this session, we are going to talk about how to use these primitives for distributed coordination use cases. Okay, let's start with a bit of talking about distributed coordination. Nowadays, almost any software we develop runs in a distributed setting, right? We deploy web applications, microservices, distributed databases, data processing tools, etc. And so this is how Amazon's microservices looked like 11 years ago, and I cannot even imagine how it looks for now, right? So when we have such a system, we always need a certain kind of tasks to coordinate components of our system. So we call these tasks, distributed coordination. For instance, we run multiple instances of some service for redundancy and elect one of them as the leader, and the leader becomes responsible for handling incoming requests, or we coordinate our processes while trying to accessing to a shared resource like a file system maybe, or we track who is alive in the cluster so that we can perform some load balancing or maybe task distribution, etc. And we also manage and share some metadata about our system, like connection parameters, discovery information, application settings, feature flags, etc. And the thing is, these tasks involve a lot of complexity, and usually it's not a good idea to write your own distributed locking or leader election algorithm. So it's quite probable that your algorithm will work fine for the happy scenario, but it will contain some bugs and race conditions, and it will break down terribly in failure scenarios. So if you would leave this session with just one conclusion, so this can be it. So do not write your own leader election algorithm, or so it really doesn't make sense. We will see it in a demo in the following parts. So okay, then how can we deal with our coordination requirements? And of course, we have some tools that offer solutions to this for these problems. So these tools use leader-based consensus algorithms under the hood, so they always preserve strong consistency of the underlying data. So with respect to the cap principle, they are CP, and we usually deploy them as a central repository, and they serve to multiple applications. So in this talk, before going into our own solution, we will first have a look at a couple of these systems and investigate how their APIs evolved over time. So it all started with a paper from Google, Chubby. So this paper was published in 2006. Chubby is a distributed log service. It's used by several internal Google projects. It is not an open source project, but the paper is very good, and it explains a lot of stuff in really great detail. So if you are interested in these topics, you can definitely have a look at this one. And after Chubby, ZooKeeper was developed by Yahoo. Then it was moved to Apache. ZooKeeper is like the open source version of Chubby. Chubby's API significantly influenced ZooKeeper. And ZooKeeper uses, so I forgot to mention one thing. So Chubby was the first tool introduced for this tasks, and it was using the Paxos consensus algorithm. And after Chubby, we got ZooKeeper, and it is using another consensus algorithm, ZooKeeper Atomic Broadcast. And after ZooKeeper, another distributed coordination tool popped up. So etcd popped up in 2013 as another distributed coordination tool. So Kubernetes internally uses etcd, so it's a very good one. And it uses, again, another consensus algorithm, Raft. And the thing about etcd is etcd engineers note that they learned a lot of lessons from how ZooKeeper is built and maintained, so they made a lot of improvements over ZooKeeper while building etcd. And if you look at APIs of these systems, they all offer some sort of a strongly consistent key value store as a foundational layer. For instance, in Chubby and ZooKeeper, there are files and directories, so they offer an API like a Unix-like hierarchical file system API. So you create files and directories, and you can persist arbitrary data on these files, like discovery information, feature flags, anything. On the other hand, in order to improve or in order to achieve better performance, etcd prefers to offer a flat and ordered key value store instead of a hierarchical system. And they built their high-level primitives on top of this file system API in different ways. For instance, Chubby offers locking APIs on files, so you can directly use it, or it is directly used as a distributed lock service. You can acquire locks on files. And the paper says that having an explicit locking API is very useful because application developers are usually familiar with how to use locks, even though they may not be aware of all the consequences of or complexities of distributed systems. On the other hand, ZooKeeper does not offer any high-level API. Instead, it offers receipts. So receipts are descriptions to implement those high-level APIs like distributed locks on top of its file system API. So I didn't put an example here, but you can consider it like, the API is like Lego bricks, and these receipts are those Lego guides to build those fancy Lego figures. Follow these steps for a distributed lock, follow those steps for a barrier, etc. So it sounds quite flexible, right? Once you have a pretty solid file system API on the bottom, you can build many coordination primitives on top of it. But the thing is, even fundamental coordination primitives like distributed locks require non-trivial algorithms. So you need to make sure that you implemented everything exactly as described in the receipt. So it's not an easy task. So it's quite difficult to verify consistency of such algorithms. So because of this, Netflix engineers developed a client library for ZooKeeper, Curator. So basically, this library implements common ZooKeeper receipts behind high-level custom Java interfaces. And it seems that etcd also learned from this lesson. So etcd implemented its leader election and distributed locking primitives on top of its key value store API. So it goes without saying that all of these systems are very successful projects. They empower many mission-critical software. But based on how their APIs evolved over time, I think we can make a few comments, and I think there are a few key takeaways. So first of all, even when we have a strongly consistent key value API on the bottom, using it for distributed coordination is still quite challenging. So I think it is better if these systems offer high-level and familiar APIs to us. And secondly, when we look at these systems, they all offer some sort of APIs like locking and semaphores. So some basic primitives like locks and semaphores are useful in many coordination tasks. And if you look at the JDK, we already have them under the java.util.concurrent package for a long time, right? In JDK, we have locks, semaphore, atomic classes like atomic integer, atomic long, etc., countdown latch, and many other primitives. And we already have an idea about how to use them. And we use these primitives of JDK to deal with concurrence and non-determinism while writing multi-threaded applications. And if we look at multi-threaded applications and distributed applications, these two fundamental challenges exist in both. So it doesn't make a big difference if we run our threads in the same process or in different processes. So in both cases, we have concurrency, so they are running concurrently, and because of this, we have non-determinism. And plus, in distributed applications, we have another challenge, partial failures. So a distributed application is expected to keep running while some of its components have failed. And personally, I think dealing with partial failures is a bit more challenging than dealing with concurrency. So our idea is we can capitalize on this conceptual similarity between multi-threaded and distributed applications to make JDK's concurrency primitives useful for distributed coordination. And this is exactly what we did, actually. So we already had implementations of these primitives in our previous versions, but they were built on asynchronous replication, and they were not offering the consistency guarantee expected from them. So basically, they were not working with strong consistency. So in our new release, 3.12, we clarified their distributed execution and failure semantics and implemented them on top of the Raft consensus algorithm. And even though we follow a different approach from all other tools we mentioned here, we learned some lessons and borrowed some ideas from them. So as of now, we have distributed implementations of atomic long, atomic reference, countdown latch, semaphore, and lock primitives of JDK, and we are planning to extend this list. So fence lock is our new distributed lock implementation. It extends the lock interface of JDK. So these systems, these APIs work with strong consistency. So if your cluster splits into multiple groups because of a network problem, you will not be able to interact with these APIs on both sides of your network partition. So only one side will continue to interact with them, and by this way, we prevent their data to diverge on different sides and preserve strong consistency. And as I said earlier, these algorithms are a bit difficult to test and verify. So in this journey, Jepsen is the industry standard tool to test consistency of distributed systems. So it subjects the system into several failure modes, like network problems, crashes, restarts, clock skew, etc. And after that, it checks if the system still holds its consistency promises under those failures. So what we have been doing is we have been testing our solution with an extensive Jepsen test suite, and I can say that this approach helped us to discover many subtle bugs and improve the system. So this part is a bit related to Hazelcast. So the current set of concurrency primitives have quite small memory footprints, right? So we do not have a key value store API yet. So the state they are holding is quite small. So even if you are running Hazelcast to store large amounts of data, like with 100 servers or maybe more, you do not have to put these primitives on all of your servers. So you can just run them on a few, like 3 or 5, and we call these members CP members or CP nodes. And since consensus algorithms usually work with an odd number of nodes, like 3 and 5, maintaining majority of the system is quite important. For instance, if you run 3 servers, you can tolerate only failure of 1 server. If you run 5 servers, you can tolerate failure of only 2 servers. So maintaining the majority is quite important, and because of that, we also implemented dynamic clustering. So at runtime, if one of your CP members crash, you can remove it from the cluster and replace it with another member, or you can start another member to preserve your majority. And we also have a notion of CP groups. So the idea is, so this CP group is an independent unit, so it runs the Raft consensus algorithm independently. And what you can do is, if you want to improve your throughput, if you want to achieve higher throughput, you can distribute your concurrency primitives to multiple CP groups and run each CP group on a different set of servers. So as I said, we built this solution on top of the Raft consensus algorithm. And besides Raft, we also have the Paxos algorithm, and Paxos is around for probably 30 years and maybe more, and it also has many variations. But the thing about Paxos is it's a bit difficult to understand, and it has many gaps for implementation concerns. On the other hand, Raft is a new algorithm, a new consensus algorithm developed recently, I guess 6 or maybe 7 years ago. And its main goal is understandability. And I think it achieves this goal because it has been adapted by many successful systems like etcd, Consul, Neo4j, what else, Hazelcast, I don't know, many tools. And so it's a consensus algorithm. Basically, it gives you a strong consistency guarantee for the underlying data, and it can tolerate crash failures, network failures, timing failures. And it remains available as long as majority of your servers are alive. But besides guaranteeing strong consistency for the underlying data, it also discusses several runtime concerns, and it also allows performance optimization. So for instance, it has a solution for, what if one of your servers are, behind of the others and it want to, catch up the other servers. So it has a solution for that, snapshotting. Or what if you want to change membership of your cluster at runtime? So these stuff are a bit difficult when you are running a consensus algorithm, and Raft algorithm defines solutions for each one of them. So in fact, these concerns are also implemented for Paxos algorithm, but they are spread around several papers, solutions, etc. And the good thing about Raft is it gives you everything, as a single compact solution. And I can say that it was really helpful for us to, build our solution on top of this algorithm. So Raft implements a technique called replicated state machines. So what happens is we put a log of operations and the state machine into each server. And in our case, state machine is the implementations of these primitives. And the algorithm first elects a leader, and the leader becomes responsible for handling the operations and replicating them to other nodes in the system. And if the leader fails, there will be a new leader, so there will be another leader election, and the algorithm guarantees that there will be a single leader committing operations to the other nodes, and all nodes will run these operations in the same order and end up with the same state. Yeah, okay, we pretty much covered the basics, so I will run a couple of demos to show how this system is used in real-world scenarios. So we will run a very simple demo in the first part. So you can find my demos in this repository. So here we are mimicking a configuration management use case. But instead of having a configuration manager, updating configuration of the system and some services listening to those configurations, we will follow a different approach. So we have two roles. First, we have a pet owner process, which is publishing funny cat photos and dog photos. And we also have a web application displaying those photos. So in the initial version of this demo, I prepared the demo for the configuration management use case, but it was a bit difficult to track, so I tried to simplify it with this one. So let's see it. So this is my YAML configuration file to start my cluster. So in fact, it's a very basic configuration for Hazelcast. So it contains the networking and discovery configuration. So this solution is built on top of existing utilities of Hazelcast. And to initialize our solution, we just configure our CP member count here, 3. So we say that I will run 3 servers. And it is enough to run this solution. And the other parameters, so we will talk about the other parameters in a minute. So let's see. Let's see our domain class. So this is our domain class, the photo class. So I'm using this class to publish a new photo of my pet. So it has an ID field, which is incremented every time when I publish a new photo, and also a file name field. And for now, we can ignore this field. Again, we will talk about it later on. So this is my class to start the Hazelcast server. So it just starts the server and prints is ready log. So let's run it. So I already started my cluster to save up some time. Let's see it here. Okay, so my cluster is started with 3 members, and they already elected their leader via the Raft algorithm. So here the second server is elected as the leader, as you see, and the other servers accepted its leadership. And our service web application is printing some logs because we are not publishing new photos. So let's start my, oh, okay, I forgot to, okay, so this is my class to publish new photos. So I will run this class and it will publish some photos for my cats and dogs. So here I'm using an Hazelcast client to connect my cluster. Then I am fetching two primitives. So the first one is an atomic reference. So it's a distributed version of JDK's atomic reference. And we also have a countdown latch. So here is what I'm doing. So first I'm creating a new photo. I'm choosing a random picture for that. And then I'm setting this photo into this atomic reference field. So from now on, our web application can read this atomic reference instance and access to that photo. But in order to notify my web application, I am using the countdown latch as a basic notification mechanism. So I am calling the countdown method here. So in fact, my web application is awaiting on this latch. And when I call the countdown, it will be notified and it will understand that, okay, there's a new photo, and then it will read the value I set here. So let's see the other side. So this is my web application. It's a very basic Spring Boot application, actually. And here is the service class for that. So here I'm starting a background thread. And this thread is doing exactly the reverse of what we are doing in the pet owner. So first, I'm awaiting on this latch with a timeout. So this call will return either when 5 seconds pass or the pet owner notifies me. And after that, I just read the last published photo from this atomic reference instance, and I put it into a local field in order to cache it. So when my HTTP controller asks for the last published photo, I will just serve it from the local field. And okay, now we can go back to the console. Yeah, okay, my cluster is up and running. I will start my pet owner process. Okay, let's make it publish dog photos. Just a second. Okay, so it started. So now we have our pet owner process publishing new photos. So the blue lines are printed by the pet owner, and the brownish lines are printed by the web application. So it's better to see it on the browser, actually. So here, so every 2 to 3 seconds, we are receiving a new photo. So basically, what we did here is we used two basic primitives to share some information about, share some information between different components of our system. Okay, we can go back to our slides, but let's kill this guy first. Okay, so this was the first part, and before going into the second part of the demos, let's talk about our new distributed lock implementation. So fence lock is the distributed version of the lock interface that exists in JDK. And so the good thing about having the Raft consensus algorithm under the hood is we do not have to worry about consistency of the lock state, right? So it will preserve strong consistency during network partitions, and it will remain available on one side of the network in case of failures, network failures. And you can use it for fine-grained locking scenarios, like acquire the lock, perform some operation, and release it, and someone else can acquire it again. Or we can also use it for coarse-grained locking, like leader election. So I will acquire the lock, and I will be the leader, and probably I will remain as the leader for maybe weeks, months, until I fail, right? So it is suitable for both cases. But if we talk about distributed locking, consistency of the lock state is not the only concern for us. So there is another critical participant in these scenarios, our clients or lock holders. For instance, a client can acquire the lock and then it can fail, without releasing it. In such a case, if we do not release the lock automatically, the lock will remain unavailable forever, right? And our application will suffer from this problem. Probably we will lose some availability and we will get some timeouts, etc. So in order to deal with failures of clients or lock holders, so we introduced a session mechanism to track their liveness. So what happens is when a client makes its very first lock request, it will start a new session on the server. And after that, all lock requests of this client will be associated with that session. And after that, if the client is not interacting with the system, maybe it is busy with performing some other work, so we will be committing some session heartbeats in the background to keep its session alive. So it all happens behind the scenes. And if the system does not receive any heartbeat for some time, it will just assume that, okay, owner of this session is crashed, so I will just kill this session and I will release all the locks associated with this session. And the very same logic also works for the semaphore and the permits. So in the first part, we had a drawback. Our pet owner process was, we just run a single instance of the pet owner process, and it is a single point of failure, right? If it crashes, there will be no other process updating or publishing new photos. So we can even see it. So I just killed it here, and as you see, there is no new photo popping up, right? And if it was a stateless process, maybe it can be easy to just restart the process, but it can be a heavyweight process, or the restart procedure can be a bit difficult, or it can be a stateful process, so it may not be so easy to restart it, etc. So in this second part, we will eliminate this drawback by running multiple instances of our pet owner, and we will use a fence lock to make a leader election among them. So let's see that in demo. Okay. So this is my second version of the pet owner code. So this time I will run multiple instances of this class. And here I'm using another primitive. So I'm using our fence lock. So before starting to publish new photos, first I'm attempting to acquire the lock. So when we run multiple instances of this class, only one of them will be able to pass this line, and it will be the leader, and the other one will be awaiting on this lock call. And after I get the lock, it means that I am the leader now, so I will start publishing new pet photos as before. So let's see that. I will run okay, let's make it publish cat photos this time, and let's make it published though. Okay, so our cat owner already acquired the lock and it started publishing new cat photos, and let's wait for the other one. Okay, so the other process is awaiting on the lock call. So if we check our browser, so we will see that we are getting new cat photos every 2 to 3 seconds. So basically what we are doing here is we started multiple instances of some process, and we used our fence lock to make a leader election among them. And in this demo, we configured our session timeout to 15 seconds. So it was the configuration I used here. And it's a bit aggressive value for production usage because it's too low for production usage, but I use it here only for demonstration purposes. So let's see our failure scenarios now. So I'm just crashing the current leader, and I will wait for some time until the system decides that, okay, the leader is gone, now I will release this lock and give it to the other process. So the next photo will be a cat photo because our lock will be released in a moment. Yes. Okay, now the lock is given to the other process, and now we have a new leader. So far, so good. So again, to repeat, in this demo, we used the fence lock to make a leader election, and we relied on session semantics to recover the lock when the leader fails. But as I said, 15 seconds was a bit aggressive configuration, right? It is too small, and in production, it can happen that, for instance, a leader or a lock owner can encounter a long garbage collection pause, or maybe it can temporarily disconnect from the cluster because of some network problem or configuration problem, etc. And in such a case, if we release its lock and if it comes back alive, it may not notice that it has lost ownership of the lock, right? And we can actually mimic it in our scenario because here I didn't actually crash the previous leader, I just freezed its process, so I will just resume it here. And now we have two processes, both think that they are the leader. So if we check the UI, so as you see, photos are alternating between cats and dogs. So this is not a good situation for us because we have two leaders now. Okay, let's just stop these processes for now. If we want to prevent such situation, we can use a longer session timeout, or maybe an infinite one. But if we use a very long session timeout, then it will create a liveness problem for us because even if a client actually crashes, it will take some time until we decide to close its session and release the log. But just as in this scenario, if we use a very small value, it means that we can prematurely close a session and assign the log to someone else. So in such a case, we will break safety of the system. So the session semantics, or making a timing assumption like this, offers us a trade-off between safety and liveness properties. And in our asynchronous distributed systems, we cannot do better than this because it all boils down to the fact that we cannot make 100% reliable timing assumptions in our systems. But of course, we are offering another mechanism to deal with this problem without sacrificing safety or liveness. So what we are doing is we can order our log holders, or we are order our clients by assigning some monotonic fencing tokens to them. So each fencing token is just a number. So it increases each time the log is, the log moves from the available state to the held state. So it increases each time the log is given to someone. And when I acquire the log, I get a fencing token, so I get a number, and I can pass this token to the external services to invalidate requests of previous log holders. And we will see it in a demo, so it will be easier to follow. We named our solution fence log after the terminology Martin Klapman used in his How to Do Distributed Locking blog post. So if you're, if you want to learn more about this stuff, you can definitely check his blog post. And we also published our blog post about fence log to explain all the details about how to use it in a distributed locking protocol and how to make your own components interact with the locking protocol. So we will see it here in a demo now. So let me show you the last version of my pet owner class. So this is the last version of my pet owner class. Again, we will run multiple instances of this one. So here we are using a fence log again, and this time we are using another method to acquire the log. So when I get the log, this time it gives me a token, a fencing token. Now I'm using this token to, so here, so this was the field we didn't mention, or we didn't explain initially, so I'm using this field here. So when I acquire the log, I pass my token to the photos I am publishing. And after that, I check if the last published photo contains a fencing token bigger than mine. So if this is the case, it means that somehow I lost ownership of the log and the log is given to someone else because someone else has a bigger token. So when I detect this situation, I decide that, okay, I'm no longer the log owner, and I step back. I just terminate myself here. So I just, shut down. Okay, let's see it. Okay, let's make this one and publish dog photos, and I'm running the second one again. And let's make it publish cat photos. Okay, so the dog owner already acquired the log, and the cat owner is waiting on the log call now, so we can see it here. So, okay, here is our fencing token. So the current leader is publishing dog photos, and its fencing token is 1962. So I will just freeze its process and wait until the log is given to the other guy. So we will see that in a second that we will have a new leader publishing cat photos, and we will also see a larger fencing token. Yeah, here it is. So now we have a new leader, and it received a larger fencing token bigger than the previous one, and I will just resume the process I freezed, and as you see, it just terminated itself. So we can check the logs, and we will see that, okay, this is the last log line it printed before killing itself. So it basically says that, okay, my fencing token was 1962, and the last photo in the system is bigger than 1962. So it means that I no longer hold the lock, so I'm just going away. Yeah, okay, this was all about the demo part. So to recap our discussion, so again, I will say that, do not write your own distributed locking algorithms, distributed coordination algorithms, try to avoid it as much as possible. And it would be much better if you use high-level and familiar APIs that hide complexities of, all of this stuff. And, in this session, I mostly focused on the API part. We didn't mention network, we didn't run any demo about network partitions and etc. But, they bring much more complexity. So we try to, offer high-level APIs by implementing distributed versions of this java.util.concurrent primitives, and hiding all of these complexities behind well-known and simple abstractions like Java locks, semaphores, countdown latches, etc. And in these systems, operational simplicity is also another important concern, because these are a bit heavyweight systems, so they run a consensus algorithm under the hood, and you need to keep your majority of nodes to be up and running. And you need to be able to scale up your workload. So because of that, dynamic clustering and horizontal scalability is quite important, in my opinion. So we enabled these two features from day one in our solution. And so we are planning to extend our API by implementing a key value store and also an event mechanism. And it will be much easier to run those demos or implement those demos we saw, because you will not have to write custom domain classes like photo. You can just use the key value store to store arbitrary fields, and also you do not have to poll the system to get the changes. Instead, with this event mechanism, the system can push you the changes. So this part is existing in the other tools, but we didn't implement them yet. So we are working on them. And we are also planning to work on disk persistence. So the Hazelcast is an in-memory product in general. So the current solution of this primitives also works in memory. So you can use the dynamic clustering feature to deal with failures. So if a member crashes, you can just replace it with another member by just starting a new server, or promoting another member to this CP role. But once we have disk persistence, so it means that if a member crashes, you can just restart it, and it will work like nothing happened. So it will improve resilience of this solution. And we are also working on the tooling part. So we have a management center, a web UI to manage the Hazelcast cluster, and we are integrating this solution with that tool. And we are also working, we didn't start actually, we are planning to work on a command line interface for this primitive suite. So you can find my demos in this repository, and so you can just check out the repository and run the demos on your computer. So I tried to explain all the steps. And in these demos, I just focused on the API part and didn't run any demos for horizontal scalability or member failures, etc. But if you want to learn more about them, you can just check the documentation and code samples. So we try to explain them in detail. And also, I'm writing blog posts on our website about this stuff. So if you're interested, you can check my blog post as well. And of course, if you want to try it, just add Hazelcast dependency to your Maven POM file, and you are good to go. And if it would be much better for us if you come back with some feedback about usability, or maybe bug reports, right? So that's all for my session. So thank you for your attendance. I hope you enjoyed it. I'm having a good time here. So if you have any questions, I can answer them here, or we can talk outside after the session as well.
Hi. My question is, can you a little bit overview what what is using underneath of Hazelcast? Do you use any, I don't know, zero MQ to iterate to each nodes? What do you use inside underneath of Hazelcast, basically?
Sorry, can you repeat your question? I couldn't follow. What we are using inside Hazelcast?
Yeah.
To implement this? Or what?
Yeah, how does it implement it?
Okay.
What is the architecture of
Yeah,
nodes?
okay. So we have our own internal RPC mechanism inside the cluster. So Hazelcast servers, communicates with each other with this RPC mechanism, and we implemented the Raft algorithm, inside this RPC mechanism, and then on top of it, we coded the state machines of these primitives. So for instance, let me show you the logs here. So, just a second. No, whatever. Sorry. So for instance, I'm running multiple Hazelcast servers, and one of them will be elected as the leader, so they will run this Raft consensus algorithm inside this RPC mechanism. And after that, when I make for instance, log call from my client, I will be connecting to that server, which is the leader of the Raft, that consensus group, the CP group. I mean, then, I send my operation to that member, and it will replicate this operation to the others via this RPC mechanism that runs the Raft algorithm. Then after that, it will send me the response. So I'm not sure if this answers your question, but we can talk after. Yeah.
So if it's RPC, it means that it's completely blocking, right? So
yes, yeah. But we also have asynchronous versions for some of these primitives, like atomic long, atomic reference. So there are also async calls. So you can make an async call, and it will call you. It will give you a callback. So in fact, you provide your callback, and once the RPC is done, it calls your callback. But it's not available for all APIs. For instance, locking is a blocking thing, right? So if you want to acquire the lock, you wait until you get it. At least it is, we implement it in that way in our implementation, because this is the distributed version of the lock interface. In fact, this is how Java locks work, right? So you make a lock call and you wait until you acquire the lock, or you make a try lock call and give a timeout. And in that case, again you will block for like 10 seconds, or whatever you give to the timeout value, and after that, the call will return. So in either case, some of the APIs are blocking, and some others have asynchronous versions. Yeah, sure. Other question?
Is there any questions?
So, is the Hazelcast built on top of this library, or is it just some third-party library which is used for some other reasons? I mean, Hazelcast as a internal in-memory data grid, does it use this library internally?
Actually, this library uses Hazelcast internally, so it's the other way around. So we already have Hazelcast for 10 years, and we didn't have this implementation, so the Raft implementation. We had our own RPC mechanisms, etc. to, so basically it's a distributed cache, so you can use it for, I don't know, storing terabytes of data. So we have users with such deployments, and we built this library inside existing mechanisms of Hazelcast. So we have the Raft algorithm implementation inside, and we integrated it with the RPC mechanism that already exists in Hazelcast.
Right, and that means that for commercial use, this library is not free, right?
No, this is open source, completely open source. Yeah. We also have an enterprise version, but this part is, everything I mentioned in this talk exists in the open source, so you can use it for free.
Thank you.
Yeah, sure. Yeah, okay, I guess we are done. Thanks again.